Good morning, friends. Through this series of videos, we wanted to cover how Kubernetes and cloud-native applications are tied together. What exactly is cloud-native application? How it is different from monolithic application? What are monolithic applications? What are the drawbacks of monolithic applications? Why monolithic application design in the way they were designed? See, we wanted to answer all of this question. We wanted to understand the motivation behind why we need cloud native applications. And once we get to know why cloud native applications are needed, we will talk about what are the challenges around managing these cloud native applications. And then we will talk about how Kubernetes helps in that. In the later part of the series, we will cover the deployment of Kubernetes in multiple environments, including bare metal, VMs, um, local cloud, something like OpenStack, public clouds, something like AWS, Azure, Google, etc. So we would like to cover all the popular variants of Kubernetes deployment, and we will talk about the challenges faced in each and every cases, which one is more easy for a particular use cases. So we aspire to cover all of those things. So please subscribe to this channel so that we can build more such videos. And please add your comments as we go along and ask your questions. If you find something in the video is not clear, we would like to answer all of those things. So with that, let's first start with the monolithic application and try to understand what exactly it is. So what is monolith application? So monolith application, you can think of a big giant application which may be multi-threaded, which may not be multi-threaded. But the point is a monolithic application would be running as a single process. Okay. And it would be a single piece of software which would move in that all the pieces of software which combined together makes this application are actually running as a single process. Okay. Just think of any application of significant size, and if you have been around and if you know like how that application has been built up as a single process, if you have been in the industry for let's say more than 5 or 10 years, you must have some experience with such applications. So for example, Firefox is one such application which is too heavy, right? And it is a single process. Yes, it is multi-threaded, but it is single process, and it has been designed earlier, it has been designed as a monolith application. Okay. Similarly, if you think of the early phases of the operating system, they were all monolith way of designing, and then slowly and slowly they migrated towards the microkernel approach and then segregated things apart. Okay. So what are the problem with a monolith application? I mean, first of all, it is a very big piece of software. So anytime you want to make any kind of change, you will have to go to this big piece of software. You will have to identify what part of it has to be changed, and then most likely the interfaces to that piece of software with the rest of the software is not very clearly defined. So you will have to guess basically, okay, what exactly it is going to affect because of this change, right? Now think of the other use case. If you want to scale things further, right? Now, because this again is a single piece of software, and let's say of the overall software, there's a specific piece which is becoming a bottleneck, and that only is the piece which you want to scale, and you want to keep rest of the things same. Is it possible? Generally, it turns out to be difficult with the monolith application because again, it is a single piece of software. So if you want to scale something, you will have to deploy another stance of the software, right? So if you really think about it, like how do you upgrade the application? Okay, you will have to turn it down. You will have to create a new version of the software. You will have to deploy a new version of the software, and there will be a downtime associated with this. Okay. Also, because of this monolith application, the entire application have to be running on a single system. Of course, you can run multiple instances of the application on different systems, different hardware, but one single instance of application cannot span across multiple servers. Okay, so look, for example, if you created an application which let's say need 32 GB of memory and let's say 18 CPUs, which is a common thing if you are building something of industry scale, okay, and you want to deploy it. And let's say if you have a system which do not have such capacity, there is no way you can deploy this application because it has to be deployed on a single server. Even if you have 4 such servers which combined together provide you the capacity required to run this application, it cannot span across 4 servers. Okay, so these are the basic problem with the monolith application, and by design it is not supposed to be, you know, spanning across multiple servers. And so how do we do it if we have to go to clouds, right? Uh, so if you think about cloud, like what is the idea behind it? The idea behind cloud says you want to scale on demand. You do not want to reserve resources beforehand. You want to scale on demand. You want to upgrade your applications easily, and there should be minimum downtime. These are the basic requirement with which one wants to be a cloud native applications. So what was the building block of a cloud native application? Let's talk about that. So microservices. Microservices are the primary ideas around which the cloud native applications are built. Okay. So microservice-based architecture is aligned with event-driven architecture and service-oriented architecture principles, where complex applications are composed of small independent processes which communicate with each other through application programming interface over a network. APIs allow access by other internal services of the same application or external third-party services and applications. So basically here the idea is something like this, right? First of all, what you will do, instead of building one large piece of software, you will find out what are the functional block of your entire applications. Okay. Once you have decided these are the fundamental blocks of my application, you will decide, okay, how these applications need to talk to each other. What are the things they have to share with each other? Okay. Once you have decided that, you will decide the interfaces to which they will communicate, through which they will communicate. Okay, and most likely we will call those interfaces something called application programming interfaces. So what exactly is application programming interfaces? These are the interfaces through which this different application communicate with each other. Okay, one such example could be REST APIs. Okay, there could be other ways also. But the idea is now you have created a system which instead of one big software now is a combination of maybe tens of hundreds of microservices which can be spawned on demand, which provide clear interfaces to communicate with each other. Okay, and these microservices can scale independently of each other in a way that, let's say there is a microservice 1, 2, and 3. For some reason, you want to scale microservice 2, but you want to keep 1 and 3 intact. You do not want to scale them. It is perfectly possible because what you can do, you can simply scale microservice 2 and you can have a sort of load balancing application on top of this microservice so that the load can be distributed across the multiple instances of this microservice. So this is basic idea. Okay. And all of these microservices, because they are independent of each other, Okay, they are not sharing memory. They are not, uh, do not have anything in common with other microservices. And whatever is common, if the design is good, you would be sharing that either through some sort of shared database or with APIs. Okay, so that's the idea. And with that, it has become easy that you can scale your microservice across different servers. There is no such requirement that all of these microservices have to be running on the same system. Okay, so with that, let's move to the next part. Okay, so we talked about microservices and what they are. Now, what are containers? Okay, so containers are an application-centric method to deliver high-performing, scalable application on any infrastructure of your choice. So I hope some of you are aware of how virtual machines work. What is a virtual machine? It is a simulation of a hardware running underneath, right? So a virtual machine will provide you an environment where you would think as if you are running on a bare metal. So it has got dedicated resources, it has got its dedicated memory, dedicated CPUs, and all of those things, right? What container is, containers do not have that kind of, hardware uh, simulation. But what it can have is that it will provide you an environment where you would think that you are running an independent operating system. You would think it's not independent operating system. What it is actually an independent file system. So every container will maintain its own file system. And underneath that, there would be a common kernel which OS would run. Okay. So as you just think of it, there is a hardware below it. Let's call it bare metal. On top of it, you would install a operating system. It could be Red Hat, it could be Ubuntu, it could be anything, right? On top of it, you would run a something called container runtime. We will discuss it in detail sometime later. But right now, just think of it as something like it's an application, it's a process which allows this different container to run independent of each other. So these are the layers of operating system, but plus container runtime. They combine together provide an environment where container can exist independent of each other. Okay. So why we need container? We need container because let's say you have created these hundreds of microservices. Okay. And each of these microservice will depend on environment. That environment could be a particular sort of file system, operating system, um, some sort of configuration required for this. Okay, maybe some libraries, maybe some third-party dependencies. All of these could be there, right? So if you want to move or deploy a microservice from one place to another, how do you ensure that when you run this microservice somewhere else, it behaves similarly? Okay, because number of things can change, right? Once you move from one system to another, number of things can change. Your file system might change, your operating system might change, your configuration might change. So to avoid this problem, container came into picture and it said, okay, you package everything together into a single container, and instead of shipping the microservice, you ship this container. Okay, so now you're not only shipping the microservice, you're shipping the microservice plus environment required to run this microservice. Okay, so it is more likely that it will behave exactly the same way as it is behaving on the dev system or in any other running deployed system. So that's what people do in real cloud world, right? They don't scale up the microservices independent of each other. When they have to scale up, they generally scale up the containers which host these microservices. Okay, so this is what container is. So this is a utility. Okay, this is a facility. This is an innovation which allowed cloud native system to exist the way it is today. Okay. Now, some of you, if thinking, okay, we could have done this with the virtual machines also. Yes, that's possible, but the thing is, virtual machines are costly. They are resource intensive. Okay. Every virtual machine, if you spawn, you dedicated some resources to it. And even if your application is not running, it will consume those resources. Okay. But container, on the other hand, may not be dedicated any resource at all upfront. Resources will be consumed only when the application is running. Okay. And then all of this container will share the resources of the underlying hardware and underlying operating system. In that way, there is no wastage of resources because you are consuming only what you need. Okay. So that is one resource advantage we get. And the other thing is, which is also very important, VM, because they are heavyweight, every time you want to scale up another VM, or if you want to turn off a VM, it takes some time. And that time is not in milliseconds. Generally, the time in seconds. That could be 10 seconds, 30 seconds, 40 seconds, in worst case, few minutes. But in general, it is the time taken is in seconds. Okay? More than 10, 20 seconds. Whereas in the industrial scale environment, this container can come up in millisecond order. That fast it is. Okay. So in a cloud environment like AWS, generally it is a very common practice that we would find that every second they would be rolling back some updates, right? And that happens so fast based on this automated feedback mechanism that they deploy some fixes. They will check if the fix is behaving as it should, and if it is not, they will roll back the current update and they will go back to the previous version. And all of this will happen in milliseconds. Okay, this is not possible with VMs because, as I said, VM will take time in the order of seconds, and the industry or architecture is moving towards a way where it is all happening in the millisecond order. Okay, so this is what container is, and these are the advantages it provides. Okay, let's move forward. Okay, so as you can saw in the previous image, we talked about container. What are the things are needed to make a working container system? Okay, the first thing is container itself, which would be the microservices and the file system. Okay, then we have the container runtime. It would be, the implementation specific thing where we would have processes like runc or containerd or CRIO, some sort of facility which will allow operating system to manage its containers. Okay, and then a Docker image. A Docker image is the file system basically. Okay, it has your OS specific file system plus the file system or files for your microservices, the binaries and all. So all of these will be bundled together in the form of container image. In the old technology, if you think about it, it's a hard disk. It's a hard disk of your container. Okay, so that's these are the three main component which basically covers the ecosystem for a container. Okay, now as we talked about, this container can be distributed across servers for a large scale application. Okay, so typically if you think about AWS and if you think about some sort of application which is running on the cloud, whatever it is, maybe some sort of photo editing service, some sort of a AI ML application, generally they would scale big time. Okay. And there may be a cases where at any given point of time you might have thousands of microservices running. Okay. How do you deploy them? Definitely not on the same server. There would be scaled across multiple servers. Okay. And when we group these servers or the host together, okay, we call them cluster. Okay. And let's assume for the moment that somebody is scheduling these containers on these clusters. Okay. On a, on a reasonable scale size deployment, you would have multiple of such cluster, and each cluster would have hundreds of these containers. Okay. So what I would have to do if I'm managing them? First, I will have to build my cluster. Then I will have to schedule these containers on this different cluster. Then I will have to define rules, how these clusters will communicate with each other. Then I will have to define rules, how the containers within a cluster would communicate with each other. Okay, what are the security policies? Okay, all of these things I will have to decide myself. Now, this is where things becomes complicated. Okay, it is feasible, probably feasible, till the time you have one or two hosts, or one or maybe one cluster at max. Yeah, then you can define your networking rule. You can schedule different containers on different hosts, and till the time things are reasonably small in size in terms of number of microservices and number of containers, it can be managed manually. But once you go past that range, let's say you have running with more than 10 or 20 hosts, you have more than 3, 4 clusters, you have more than hundreds of containers, this manual managing of containers and microservices, it's a nightmare, right? That's the most challenging part, and that's the part where the early deployments of these cloud native applications were failing because people who were designing them, everybody was coming up with its own solution. And it's a basically distributed operating system problem because ultimately you have created an application which is distributed across multiple servers in a very high scale environment, and your goal is to make it highly available as well. Okay, so how do we solve this problem? Okay, so that's where the container orchestration system comes into place. So what is a container orchestrator? That's a tool, or let's say group of tool, or a system which allows you to configure some rule at the orchestrator level. Okay, and then orchestrator takes care of the deployment, upgrades, availability, scalability, security policy, networking, everything for you. Okay, and it can do that even if you're running, let's say, 10 containers, if you're running 100 containers, if you're running 10 hosts, if you're running 100 hosts, it does not matter. Container orchestrator knows how to deal with these kind of high load systems. Okay, so let's talk about what are the some of the famous container orchestrated system. Okay, the one is Amazon Elastic Container Service. We will talk about it briefly in later part of the series. Okay, Azure Container Instance, Azure Service Fabric, all of this we will touch base. And Kubernetes. Kubernetes is the main topic of our discussion. We will spend a lot of time describing what Kubernetes is, how it works, what are the different flavor of Kubernetes, what are the different cloud deployments for Kubernetes exist. Okay, what are third-party managed Kubernetes services, what can be self-managed Kubernetes deployment and all. So we will discuss them in detail, and then we will discuss to some detail Docker Swarm also when we get to them. Okay, but going forward, our focus will be on Kubernetes because Kubernetes itself is a very big topic. It's and most widely used system or tool to manage this high-scale container deployment. Okay. Now, Kubernetes is an open source orchestration tool. It was developed by Google. So Google was using this before they called it Kubernetes. I think they were calling it Borg. Okay. Under Borg project, they were using this system, okay, to manage the container system for Google. They were maintaining or they were using this system to build their own data center or to manage their own data center or to manage the application on top of this data center. Okay, they think about the scale to which Google works, right? And they were using this system. And that is the reason why Kubernetes becomes so popular, because if Kubernetes can handle the loads which Google deploys, then it can handle any kind of load which any other kind of application can deploy in this world. Right? That's the idea. And that's why Kubernetes becomes so much popular. Okay. And other good part about this is Google made this tool open source. Okay, so that different people can come together and help improve it further. Okay, so currently, Cloud Native Computing Foundation, CNCF, which is part of Open Linux Foundation, they are the people who manage this. Okay, and it's a large community which manages this Kubernetes system, and this is managed widely, and this is the most popular choice for container orchestrator tool. Okay,